Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, so let's move on to lesson 6.2.5, working with corresponding sides. Now is where we're going to start pulling together what we learned in 7th grade about scale drawing, scale models, in scale factor with our unit on dilations and multiplication. We're going to just start putting it all together in the next 2 lessons and do some problem solving. So, graphic artists often need to make a shape larger to use for a sign. Sometimes they need to make a shape smaller to use for a bumper sticker. They have to be sure that the shapes look the same no matter what size they are. How do artists know what the side length of a similar shape should be? That is, does it need to be larger or smaller than the original? I don't know. Let's take a look at some things. All right, so with your team or on your own, because you're watching this video, find the scale factor between each pair of similar shapes. That is, what are the sides of each original shape multiplied by to get the new shape? All right, so this is what I recommend that you do. Start by copying these shapes down, both for A and for B. You got 2 trapezoids here for A, 2 triangles, obtuse triangles to be exact, for B. And this formula can be used to help you identify what the scale factor is, because the scale factor is simply a ratio of corresponding sides with the new shape's length in the numerator and the original in the denominator. And you may recall from 7th grade when I would say that the scale factor is always based on the original shape, right? So the base goes at the bottom. So in this case, you got the new one labeled and the original one labeled, but they didn't label these 2 trapezoids, so we really don't know which one is the new or the original. So this is one of those situations where I'm like, okay, maybe we just don't even think about which one is the new and which one is the original. Let's just take corresponding sides, okay? So the corresponding sides in this situation would be the sides that are in the same location, given the 2 shapes. So in this case, the 3 corresponds to the 6 because they're the diagonal shorter sides on the right-hand side of each trapezoid. And then we can see that the base, or the lower base of this trapezoid is 6, and the upper base is 12. So, if you want to say that this is the new and that's the original, go in that direction to find the scale factor. If you want to say this is the original and this is the new, go in that direction. Or you could just list both scale factors. Because remember, the scale factors are reciprocals of each other depending on which direction you're going in. Okay? In this one, they tell us which one is the new and which one is the original. So go ahead and pause for a little bit. Fill in all of this information and then declare what is the scale factor for each one of these sets of shapes. Right, so taking a look at the 2 trapezoids. Our scale factor is either going to be 2, since 3 times 2 is 6, and 6 times 2 is 12, or if you were going in the other direction, shrinking this or reducing it, 6 is twice as much as 3, so 3 has to be half as much as 6. So if you multiply 6 times 1/2, or 12 times 1/2, you would get the respective lengths of these sides on the smaller of these 2 trapezoids. So either one of those are effective for scale factors, and I would just go as far to say this: if we knew that this was called this 2, we could then use a scale factor of 2 to find out that this is 4. And if we knew that this guy up here was, let's call it, I don't know what I want to call that. Let's call this 10, which it's not, but let's just pretend it's 10. And you could figure out what this one is by, instead of multiplying that times 2, you'd multiply it times the reciprocal and multiply times 1/2. Or I guess you could also say that you divide by 2. But I would rather, for scale factors, never speak of dividing, because that just confuses the issue. Let's just focus on multiplying either the 2 or its reciprocal, the 1/2, because dividing by 2 is the same as multiplying by 1/2. Okay, so we can figure out that this would be 5 in that instance if those were indeed the measurements. But we don't know what those are, so we're just going to leave those off there. All right, so what do we have here? If this is the new, no, yes, that's the new and this is the original. Our scale factor should be, wait, hold on for a second. Yes, that's right. This is the new, that's the original. So it started here and it got bigger. Wait, hold on. Hold on, hold on, hold on. There's some mistakes here. Okay, so see what I did. So the scale factor, depending on which direction you're going, if you're actually using the formula for the original goes in the denominator and the new goes in the numerator, then your scale factor would be 5/4, the ratio of those two sides, or in decimal form, 1.25. And if you were choosing to go in the other direction, it would be 4/5 or 8/10, 0.8. All right, so it may have been easier to recognize the scale factor between the two shapes in part A of this problem than it was to determine the scale factor of the two parts or two shapes in part B. When the sides are not even multiples of each other, like 4 and 5 in part B, it is useful to have another strategy for finding the scale factor. And so here, I guess, maybe I jumped the gun by showing you this formula, the fact that we're talking about a ratio of two sides, but that is the process that we want to use here. So there are some discussion points, and normally I would have you in your groups to have conversations and answer each one of those questions, and then we would share out in class. We don't have that situation right now, so let's just read through the questions and think about the answer to them. And I think I've already talked about a lot of this anyway. So how can we use pairs of corresponding sides to write the scale factor? Okay, so that's kind of what we did here, right? We took the corresponding sides to write the scale factor. Here, I had already simplified it, and I just think of it as a multiplication process. I didn't even use the corresponding sides for example A, but for B, we had to. And so what do we do there? We just write them as a ratio and then simplify the ratio or convert that ratio, which is a fraction, to its decimal equivalent and use that as our multiplier. Will the scale factor between the shapes be more or less than 1? Well, as we see here, depending on which direction you're going and what the corresponding sides are, it could be less than 1 or it could be greater than 1. It just depends on whether you're enlarging or reducing your image. Okay, so it could be either. And then does it matter which pair of corresponding sides that we use? And the answer to that, as we saw with example A, is no. Any sets of corresponding sides can be used, right? Any corresponding sides between similar figures can be used. So here we could have used the 6/3 is equal to 2 or 12/6 is equal to 2. If we knew what these were, we could have used those. If we knew what those were, we could have used those. Okay, so let me just point out, I'm sure I don't need to say this because you've been doing this for much of the year now, but if I go too quickly and you're not getting a chance to fill everything into your journal, please pause. Please take the time to back up. I'm sure that's fairly intuitive. Maybe I don't even have to say that, but I just feel like right now I'm thinking about students in the classroom when I rush too quickly and they're not able to write that fast. And so I probably don't even need to say that. Okay, let's just move on. All right, so a study team is working together to find the scale factor between these two triangles. Claudia set up the ratio 14/4. Isaac set up the ratio 28/8. And Paula set up the ratio of 21/6. So my question I always ask is, which one of them is right? How could they all be different? What's going on here? Okay, please take some time to pause this video and copy down each one of these rectangles and copy down each one of these ratios that Claudia, Isaac, and Paula wrote down for their scale factors. And then answer the question A and B. What did the students do differently when they found their scale factors? And do the triangles have more than one scale factor? If not, show how they are the same. Okay? Take a couple minutes to copy these down and address those two questions. All right. So what I like to do when I am looking at a couple of triangles trying to determine what the scale factor is, I like to highlight the sides that correspond to each other. So both of these triangles are oriented the same way, right? Longest side is the base for each one of them. It's at the bottom. The shortest side is in the upper left-hand side, and then the medium middle length is on the right side. So 4 and 14 correspond to each other. 8 and 28 correspond to each other, and then the 6 and the 21 correspond to each other. So you can see what they're doing here. They're taking the ratio of the corresponding sides, the new over the original, exactly how the formula was written up. Here we've got 28 over 8, new over the original, and here we've got 21 over 6, the new over the original. So what did the students do differently when they found their scale factor? Well, they just used different corresponding sides. Triangles have more than one scale factor, and if you simplify each one of those ratios, 14 over 4, 28 over 8, and 21 over 6 are all equivalent to 7 over 2, which is the same as 3.5. So no, they all have the exact same scale factor. So that kind of tells you that it doesn't really matter which side we go with, right? To find the scale factor, if we know for a fact that these two triangles are similar, then every single set of corresponding sides are going to be proportional according to a common multiplier or scale factor. So why does it make sense that the ratios are equal? Well, it's because the scale factor is the same. I mean, there's one scale factor that applies to this situation. And so whatever set of corresponding sides you use is always going to reduce down to that scale factor. All right, so Alex was working with two triangles for problem 86. He now has a few more pieces of information about the sides. He has represented the new information and his scale factor in the diagram reprinted at the right. Sketch his diagram on your paper. Okay, go ahead and pause and put that information in. You don't have to highlight it. I just chose to highlight those with the scale factor being derived from the two sets of known corresponding sides. And then I color-coded the other two sets of corresponding sides so that we can figure out our missing lengths, our x and our y. So go ahead and pause and fill those in. Alrighty, so we know the scale factor is 5 over 4. So the first set of directions is telling us to find the length of side x. So we know that side in triangle G that corresponds to the x is 6 inches long. So since our scale factor is 5.4 and h is a bigger shape than G, then we will use this scale factor, 5 over 4, and multiply it times 6. So we get 6 times 5 over 4. When we do that, remember, when you're multiplying fractions together, it's always numerator times numerator and denominator times denominator. So you want to make sure 6 gets multiplied times the 5, and the Ninja 1 denominator that we would have for the number 6 would be multiplied times the 4. So that gives you an answer of 30 over 4, which, when you simplify it down, becomes 7.5. So x has to be equal to 7.5. Now, this isn't the only way to solve these problems. If you recall last year when we were working on proportional relationships, I showed you multiple ways to solve problems. And in some situations, using a unit rate was the best way to go. In other situations, we set up a proportion and used a giant 1 or used the cross multiplication. So I'm going to show you how we can do that now. Let's set up a proportion where our corresponding sides that we know are 5 and 4. The x corresponds to the 5 because they're both in the same triangle, and the 4 corresponds to the 6. So 5 over 4 will be equivalent to x over 6. Well, do we know a giant 1 that we can use there, or should we just cross multiply? I chose to just cross multiply. And when you take 30 divided by 4, you get 7.5 for an answer. So whether you choose to use the scale factor, that multiplier, to find your new side length, or whether you choose to set up a proportion with corresponding side lengths, it doesn't really make any difference which way you do that, okay? All right, so part B, since Alex multiplied the side lengths of triangle G to get triangle H, he needs to undo the enlargement to find the side length, or the side labeled Y. What math operation would you use to undo this enlargement? Write an expression and be prepared to explain your reasoning. And then as a result of this, we're going to figure out the value for Y. Now, you could do two things, honestly. You can do the division with the scale factor, because that would undo, right? Y times something, or Y times 5/4 equals 10. So 10 divided by 5/4 will tell you what Y is equal to. Or Just multiply times the reciprocal, since dividing by 5/4 is the same as multiplying times 4/5. So that's always been my recommendation. Depending on which direction you're going, either choose a scale factor of 5/4 or 4/5. When you're going in the larger direction, multiply times 5/4 like we did here. When you're going in the smaller direction, you need to multiply times the scale factor that's less than 1. So 10 times 4/5 is going to give you your answer for y. Okay, so go ahead and figure out what that answer for y is. You might want to pause. I keep telling you that. You know what to do. Okay, so I'm going to say you paused, you figured it out, and you're ready to declare your answer, and your answer is 8. Absolutely. And maybe I should put in the units of measurement here too, since this is geometry, and I would mark you down if you didn't put those units of measurement in, and we're talking about inches. So y has to be 8 inches long, and x has to be 7.5 inches long. All right, so this, I believe, is our last problem. It is. What you need to do is you need to copy down each one of these sets of shapes. Okay, if this looks a little bit busy to you, you can always go to the online book, go to problem number 90 in lesson 6.2.5, and you've got some clean examples of these shapes with all of the side links in there. I just decided to highlight corresponding sides that are known to drive our scale factor for each one of these situations. Okay, so take some time, copy these down, and for each of these problems, you've got at least 2 unknown sides. C and D has 3 unknown sides. Go ahead and solve for each one of those unknown sides. And when you're ready to check the answers, unpause. Alrighty, so let's see how you did. The 2 triangles in problem 90A. Our scale factor, depending on which direction you're going, is either going to be 3 or 1/3. Okay, I just wrote down the scale factor of 3, but it could be 3 or 1/3 because 3 times 11 is 33, and 33 times 1/3 is 11. So when we are trying to figure out y, we're going to have to multiply times 3. And when we are trying to figure out x, we are going to multiply times 1/3 or divide by 3. Okay, so our answer for x has to be 13 because 39 times 1/3 or divided by 3 is 13. And 9 times 3 is 27, so y has to be equal to 27. In this situation, that's a little bit trickier. I'm going to use my calculator. 24 divided by 9 is equal to what? 2.6 repeated. All right, so 2.6 repeated is the same. If you did this in a fraction form, 2.6 repeated is 2 2/3, which is the same as 8/3. So if you had said that your scale factors were either 8/3 or 3/8, that would also be correct. Okay, so I think I declared it as 2.6 repeated, and our 2 side lengths, x would be 16, because 6 times 2.3 repeated, let's go ahead and figure that out. That times 6 is going to be 6, stop it, equals 16. Wait, oh, there's the 16 right there. Let's do that again. 2.6 repeated. Boom, 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 boom. Is that enough? Yep. Times 6. Why is it doing that? It's so weird. You know what? I don't like you, calculator. Come over to here. This is getting bigger, so we would take 6/1 times 8/3, which is equal to 48/3, and 48 divided by 3 is indeed 16. And then if we take 24, which is our known one here. Oh, you know what you might be asking right now? How does 24 compare to y? How does that correspond? Well, the thing is, these are parallelograms. So if that's 24, this is 24. So that's why it would correspond to the y, because it would be this 24. Technically, that would correspond. But then now that I'm noticing it, if this is 9, doesn't that mean that has to be 9 as well? So yeah, y's got to be equal to 9. but let's show the work anyway. 24 over 1 times, and this is getting smaller, 3 over 8. So we end up with 72 over 8, which is equal to 9. All right, so what do we have going on for part C? The scale factor for part C is, what do you multiply times 10 to give you 25? It's 2.5. So we're going to take and let's do 35 and x correspond to each other, and y corresponds to this 25 right here, and then z is going to correspond to 8. So when you multiply, let's see, when you multiply 8 times 2.5, that's going to give you z, which is 20. When you take 17.5 and divide it by 2.5, you're going to get 7. And do you notice how these two are the same, 25 and 25, which means this has to be 10 anyway. But 25 divided by 2.5 is going to get you 10. And then for the last set, it looks like our scale factor is 1.5. And so let's look and see where we have our corresponding sides. X corresponds to the 6. Y will correspond to the 12. And Z will correspond to the 5.7. And we end up with, what do we go? 6 times 1.5 gives you X. So that's going to be 6 times 1.5 is 9. 12 divided by 1.5 is going to give you y. So that's going to be an 8. And then 5.7 divided by 1.5 ends up giving you the answer of 3.8. Okay, so I did not show all the work here. I'm hoping you got the correct answers, or if you got wrong answers, you've listened to my descriptions and you're able to figure out where you made your mistake. But if there's ever a time when there was a problem there where you didn't understand how I got the answer and you need me to go into a little more detail about how to show that work, please don't hesitate to contact me and we'll spend some time talking about it and looking that over. All right, 22 minutes. That was the shortest lesson I've had for a little while. That was good. I think the next one's going to be even shorter. I'm hopeful. All right, take care.
Hey, feeling good.